This is a video summarizing the energy changes that are associated with phase changes. I'm going to use water as an example, but it could be phase changes of any substance because everything would have a graph that looks like this. The only difference is the melting and boiling points will be at different temperatures depending upon the substance that you're talking about. So I have three formulas on this piece of paper. One, notice I underlined three things, but that's really always the same formula. Then 2 and 3. So the three formulas there on the piece of paper. And what we're going to do is look at how we would use those formulas to calculate energy changes during phase changes of water. So I'm going to make up a sample problem to work, and then I'll show you how the formulas apply. Suppose we have 100 grams of water at negative 30 degrees C. So I want to, and suppose then we want to raise that to 115 degrees C. So we're going to take this 100 grams of water. By the way, at negative 30, what phase of matter would water be in? Well, since water freezes at 0, negative 30 is going to be down here somewhere, and that's going to be in the solid phase. So we're really talking about some really cold ice. Now we're going to raise the temperature of this water, so we're going to start heating this ice until we get way up here to 115 degrees. So here's how you would calculate the energy that it takes to do that. In the first step, you're going to take this solid ice, so visualize ice like in the pan I had sitting on the stove the other day. I've got this ice at negative 30, and we're going to raise that temperature up to where it begins to melt. So since there is a temperature change, we have to use the formula that has temperature change in it. So it's going to be Q is equal to mCp delta T. M stands for mass, and we said that was 100 grams. Cp stands for specific heat capacity. On this piece of paper, I have the specific heat capacities listed down at the bottom, so I'll show you where they come from. The Cp for ice is 0.5, so we're looking at 0.5 calories per gram. The change in temperature from negative 30 to the freezing point is a 30-degree change, because from negative 30 up to 0 is a difference of 30. Delta in science means change. That is, Greek letter delta means change. So that's 30 degrees C. Notice, this is calories per gram degrees C. I left that part of it off. So now you see C's cancel and grams cancel, so you end up with 100 times 0.5 times 30. So just showing that on a calculator. Come over here, 100 times 0.5 times 30, and that gives us 1,500 calories. So what that means is it takes 1,500 calories of energy to make the temperature of the ice raise from negative 30 up to 0. But we're not even close to that 115. So the next step in the process is melting the ice. And I'm going to put phase changes over here. I'll call these temperature change, delta T's, and these are phase changes. So I'll put the phase changes in blue. All right, so we have the first phase change. You got to go from solid to liquid. So you're going to cross this line. While you're crossing the line, temperature does not change. Remember the demonstration from a previous video. So while you're crossing the line, temperature does not change. We have Q equals mass times heat of fusion. All right, so the mass is still 100 grams. The heat of fusion that we're given down here is 80 calories per gram. So 100 times 80 is 8,000 calories. Showing you on a calculator, 100 times 80, boom, 8,000. All right, so now we've raised the temperature in pink up here. We've crossed in blue. So now we're at this point. So our next step is to go to 100. So since this is a temperature change, I'm going to go to pink again. Remember, I'm putting temperature changes in pink. So mCp delta T, that's our formula for Q. The mass is still 100 grams. Specific heat capacity for water is 1 calorie per gram degree centigrade. And the change in temperature from here up to the next flat line is 100 because you're starting at 100, or starting at 0 and going to 100. So you have a 100-degree change. So now using our calculator again, 100 times 1 times 100 is 10,000. Units calories, because grams again cancel. All right, so now we've in step 1, we found how much energy it takes to get to up from here to here. Step 2, how much energy it takes across that line. Step 3, how much energy it takes to raise up to 100 degrees. Step 4, we've got to cross this line. And that's going to be the biggest amount of energy because it takes a whole lot of energy to make a liquid become a gas. And that's what's happening here. So Q is equal to mass times heat of vaporization. So we have 100 grams again, that didn't change. And the heat of vaporization, we can see listed over here, is 540 calories per gram. So 100 times 540 is 54,000. Takes a lot of energy to make that water boil away. So now we've calculated how much energy it takes to get from negative 30 up to here. Step 1 here, step 2 here, step 3 here, step 4 here. Now we're ready for step 5. So step 5 is the temperature change again. So we have Q equals mCp delta T. Mass is still 100 grams. Cp is, for steam, it's 0.5. And the change in temperature up at the top there, see, we're starting at 100 and we're going to 115, so how far is that? That's just a 15-degree change. So we have 100 times 0.5 times 15, 750 calories. So now we've done our 5 calculations. We found out in step 1, in order to go from negative 30 up to where it begins to melt, it took 1,500 calories. And then to cross this melting line, we needed to put in 8,000 calories. Then to raise our temperature from 0 up to 100, it would take 10,000 calories. To move across the boiling line, well, in other words, we had to put energy in to make it boil, but the temperature doesn't change while it is boiling. Remember the graph I made in a previous video. It takes 54,000 calories to boil it. And then to get the final little boost up to 115, it only took 750 more calories. So our total amount of energy it takes to get from here all the way up to there would be the sum of all these energies. So I would have 1,500 plus 8,000 plus 10,000 plus 54,000 plus 750. So we get 74,250. Which sounds like a huge number because we know about calories from our everyday life. These are the same kind of calories that are in food. But if you remember in the earlier videos, I told you that food calories were really kilocalories. So if I change that into food calories, put a capital C up here for kilocalories, one of those is 1,000 of those. So really, put my answer up here and keep it on screen. We're really looking at 74.25 big C calories, or food calories. So that would be about 1/3 of a candy bar that it would take to make 100 grams of water go from negative 30 to 115. So a candy bar contains about 220 or 30 calories, so that's about 1/3 of it. Okay, I think I want to stop this video at that point. That's how you handle phase changes. I might add one more comment. If we had not gone up to 115, let's suppose we'd only gone up to, say, 75, which would be right here. How many steps would we have had in the problem? Well, if we're going to go from -30, we'd still have to get it at the melting. We'd still have to melt it. But then when we got to the third step, that would be our last step in this problem. So there would only be 3 steps. And this change in temperature, if I called that 75 degrees C, then the delta T in this step, instead of being 100, would have only been 75. So you can have variations on these problems depending upon the temperature that you're starting and where you start and where you end. So that would have only been a 3-step problem. All right, that's the end of that video about energy changes during phase changes.